That's good.
All right, so I posted another homework on Canvas. I'm not sure if you guys saw it. The deadline is Tuesday. It's just two problems on the concept that it's kind of similar problems, and there's one in the midterm, so maybe it's a good practice for you to do these two problems. We have one homework left based on this lecture and next lecture. So this is, I believe, one of the most heaviest lecture in the semester, or this one and the next one. So I need your full attention because stiffness matrix and the stiffness method and all this, it has a lot of mass, a lot of matrices. I know that we're engineers, we should do math, but somehow civil engineers, they don't like math so much. But it is what it is, and we have to do it. Stiffness method is really, really important because this is what the software is doing. Like if you want to develop, this is the best way that matches the software. Like if you want to code or program, because coding is very good with matrices. So you have a bunch of matrices, you keep collecting them together to make a structure matrix. That's what the software is do. So if you want to know what is SAP 2000 is doing, that is what is SAP 2000 is doing. And the method of finite element is the same thing. It's also a bunch of matrices and nodes and degrees of freedom. So that's what the software is doing, all right? So we talked last time about the method, about the stiffness method. So, but we only talked about springs, okay? So today we are gonna talk about trusses and frames, okay? Does anybody have any question? Yeah.
I have a question about the homework, the one that's due today. The first problem, it says hand calculation. Does it mean like hand calculation for a deflection or?
I mean like don't use software.
Oh.
Does it have, do you hand calculation and use SAP 2000?
No.
Or, no. Okay, so that means that I think this is, you're going to use the method, the consistent redundant method.
The flexibility approach.
The flexibility approach. The flexibility approach is the same, like it's the same thing, like the consistent redundant.
Can we use the
Software?
steel manual to get the formula for the deflection?
Like the beam tables?
Beam
Well,
deflection?
the thing is you have to use the method, but if you want to double check, you can double check with the formula. By the way, in the exam, if I told you to use a specific method and use something else, you're gonna lose the point. So that's why, I told you to do the flexibility and you use double integration method or you use other methods, it's not gonna work because I'm testing in a specific method. Yeah.
I was using there's like some tables that we use for the PE in the structural handbook that has it's like basically like a bunch of cases where we have like different like beams.
Yeah.
And I used one of those because honestly I went to the table 8.3 and honestly none of them were giving me the answer. So I just decided to use like one case that it was like.
I don't understand what exactly you used. Like you used the table that have I don't know, reactions or deformation for specific, yeah.
The problem with the first one specifically is that the moment diagram, they don't match the tables we use for the virtual work. So the other way to calculate would be like the double integration to get the deflection and then use the.
Okay, let me double check it and I'm gonna let you guys maybe an announcement or something. This is the first problem in the homework?
Yeah.
Okay, all right, maybe I'll check after the class
Okay.
today. Right? Okay, so let's today talk about the stiffness method for different types of structure. Last time we talked about springs, and today we're gonna talk about trusses and frames. But by the way, it is the same concept. Like for example, last time we had a spring like this, and I told you to find the stiffness matrix of this spring. By the way, the stiffness matrix is unstable. It's for unstable structure. Because the thing is, we assume that there is 2 degrees of freedom at the spring. That means this spring is in the air. So all the stiffness matrix for element stiffness matrix, it's an unstable element. It's like an element in there. Like this spring is free from here and free from here. Like it has degrees of freedom to move. That's not our structure. What makes it stable is when we put this spring with a bunch of springs and we put boundary conditions, it makes the whole structure stable. So that's why in the stiffness matrix, we put zeros. That means there's no degrees of freedom, so this is canceled. And there's only degree of freedom at some elements, okay? So this applies for all structures. Okay, so let's talk about trusses. Like sometimes, like let's say I have a truss like this, and I have, let's say a ruler, and I have something like this. Can you guys tell me how many degrees of freedom this structure has as a truss? Definitely there's one here, and
Rotation.
one here, 2, 3, 4, and 5. I'm not going to consider this as degrees of freedom because I'm going to assume that these two members are not intersecting with each other. Okay? So this is the structure's degrees of freedom. To handle trusses, that mean this point can move up and down and can move left and right, right? So if I take one of these members out, like I'm going to take one member like this, and I want to develop a stiffness matrix for this member. So I have to assume when I develop a stiffness matrix for this member that this member is free in the air, like it can't move anywhere. So I'm gonna assume U1, U2, U3, and U4. That is the 4 degrees of freedom. Is this a structure? This structure is stable and determinate? No, that's like a free structure. Okay? All right, so let's see how we can develop a stiffness matrix for a member like this. So the way to do it, since it has degrees of freedom, I have to take this and fix all the degrees of freedom. So I'm gonna take this member and fix all the degrees of freedom. That's how we develop a stiffness matrix for any member. I fix all the degrees of freedom. And then, since I have 4 degrees of freedom, I'm gonna make 4 of this truss member. All right, one by one, I'm gonna apply. Do you guys remember we apply unit deformation at each one of these degrees of freedom, one at a time? Okay, because this is how we get a stiffness. So stiffness is a force per unit deformation. So if we apply it, the unit deformation, so the force is gonna be equal to the stiffness. Okay, so U1, I'm gonna make U1 equal to 1, and all the degrees of freedom is 0. U2, I'm gonna make U2 equal to 1 and all the degrees of freedom is 0. Then here, I'm gonna make U3 equal to 1 and all the degrees of freedom is 0. Same thing here, U4 equal to 1 and all the degrees of freedom is 0. Then, once I find the reactions for this, I'm gonna end up with K, a stiffness matrix, 4 by 4, because I have 4 degrees of freedom. And I'm gonna have here K11, K12, K13, and K14. Then here, K21, K22, K23, and K24. The first number is the number of rows, and the second number is the number of columns. So K21, that means in row number 2 and column number 1. So here, K31, K32, K33, K34, K41, K42, K43, and K44. By the way, the diagonal one is the stiffness force in the direction of the degrees of freedom. How? Okay, so right now, you need a force to compress this member that way, and then you are gonna have a reaction that way, right? So the force here, K is gonna be equal to K11. We need to find what is the value of K11. The value of K11 is the axial stiffness of this member. It's like a spring. If you guys remember last time we had a spring like this and we had to compress it. So to compress it, 1 unit displacement, so you have to overcome the stiffness K. So if this delta equal to 1, so B equal K multiplied by delta, K multiplied by 1 is gonna be equal to K, right? So the same thing, the spring actually is a truss member. This spring is a truss member, same thing. So K11 is gonna be equal to the axial stiffness of this member K. But let's actually convert this K. Let's try to find the value of K. What is the value of K of the axial stiffness of a member? Like let's say you have an axial member subjected to the load B and is gonna have a delta, this delta, and we're gonna say that this has is like a spring K has a stiffness. We know that B equal K multiplied by delta, right? B is a force, and we know that the force is equal to, like if you have a stress, if you wanna find the stress on this, is gonna be equal to B over A, force over area. So if you wanna find B, so B is equal to sigma multiplied by the area. The stress on the cross section multiplied by the area of the cross section. So I can put this sigma A. And K, this is what I want to find out. Delta, we can get it from the strain. We know that the strain is equal to the delta, the deformation over the length L, right? So delta is equal to epsilon multiplied by L. So I can say this is epsilon multiplied by L. So K is going to be equal to sigma A over epsilon multiplied by L. We know that there is something called Young's modulus. The Young's modulus is the stiffness of the material is equal to stress over strain. So basically, I can take this part and put E, so this is going to be EA over L. So the axial stiffness of a structural member K, by the way, this is just the axial stiffness. The members can have axial, can have shear, can have flexural. The axial stiffness depends on the Young's modulus of the cross section and the area of the cross section over the length of the member. If the Young's modulus of the material is big, that means that the material is more stiff. If the cross section area is big, that means that the area that the member is very stiff. But if L is big, so it's gonna make this smaller. All right, so we know that K is equal to EA over L. So basically I can put here EA over L. And definitely we are gonna have a response from here, EA over L. So you can respond on this one. All right, did we get that? All right, if we push this one, can you guys tell me what is the reactions here and the reactions here?
Yeah, right.
The thing is, I want to find what is the reactions here and the reactions here.
0, 0.
0, right? There's nothing here because that's an axial force. If you push that way, there is no reactions that way. All right? So basically, I can put the K11, K22, so I can find the values of all these. Put them here. Okay. So basically, I can say here, EA over L, that is K11. This is K11. This is K12. This is K13. This is K14. We agreed last time how we named them. K11, because that is the at point number 1 due to unit deformation at 1. This is at
Point number 1.
point number 1, but degree of freedom number 2. But sorry, the unit deformation is at 1. So you will find all of them has 1s because the unit deformation is at 1.
Right.
But one, the second one, like the second number represent which degrees of freedom are you at. So I'm at degree of freedom 1, here I'm at degree of freedom 2, at degree of freedom 3, at degree of freedom 4. But the 1 represent where is your unit load at. Here, I'm gonna have
K2.
yeah, but let's talk about it when I finish this. So EA over L, so I'm gonna put 0, negative EA over L because this one is in the other direction, and 0. And by the way, this is a symmetric matrix, so basically I can put 0, negative EA over L, and 0, and we are gonna find out later. So any row is gonna be equal to any column. All right, how about U2 equal to 1? This is a truss member. Like, I need you to focus with me. Let me make it a little bit. All right, let's say this is a truss member, right? Okay, this truss member is hinged here and hinged here. And usually the trusses goes under small deformation, or our structure are a small deformation. and this is hinged. Let's say that you put a unit deformation here. Can you tell me what is the reaction in this structure?
The internal.
Internal reaction, like what is the external reaction if I put like a deformation here? The thing is, since this is a hinge, the hinge allows the deformation. If you want to move that way, it can move that way. So there is no internal forces are going to develop.
Internal or external?
Either both, like, because there's no internal forces, there's not going to be external forces.
There's nothing restraining.
So the thing is, since there is a hinge here, it can allow you to move. But if there is fixed, no, if you want to move that way, I'm going to resist you with a bending moment. But since we have a hinge here, this hinge can allow this member to go up and down until a specific limit. Like, don't tell me, oh, I'm gonna take this member all the way up. So definitely, but under a small deformation, we can assume that there's no internal forces are gonna be developed. So if you have a deformation that way, vertical, so all the forces are gonna be zero. This force is gonna be zero, 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 zero. Same way this one. If you take this up, it's kind of like you have a pendulum like this, and it can allow you to move that way and that way. Same thing. Like if you have a swing, the swing is attached to a hinge, and the hinge can move that way without any elongation.
If we assume self-weight of the structure, will there be internal forces but non-external in that case?
The self-weight, yeah, if I assume the same thing when we solve the trusses. If you assume the self-weight, there's definitely going to be a bending moment on the truss.
Okay.
So it's not going to be a truss member anymore. But that's what we do with trusses, is that we assume that the self-weight is very, very small compared to the external load on the structure. So that's why we don't design the truss members for bending moment, because they are very lightweight. But if you make a truss out of concrete and the concrete is really heavy, I think you should account for bending moment. All right, so this one is the same thing. You are going to end up with forces, all are equal to zero. How about this one? This one is the same thing. You need a force that way is equal to the stiffness of the member, EA over L, and definitely there's going to be a reaction here, EA over L, and the vertical forces are going to be equal to zero. So if I want to put the rest of this matrix, so this is going to be the second row, this is going to be the third row, and this is going to be the fourth row. So we take them one, or you can put them as a columns. Either you put these forces in one column or in one row. They both are gonna lead to the same result. So since this are all zeros, so you are gonna end up with 0, 0, 0. So I put this in one column.
Good.
This one is the second column. So this is negative EA over L. That's what I told you here. So you have negative EL over here is ready. Then you have 0. Then you have EA over L positive. And then you have 0. This one is all 0, 0, 0, 0. That is the stiffness matrix of a truss member. And by the way, this is the same stiffness matrix of a spring. Do you guys remember the spring from last time? K, negative K, negative K, K. It's gonna be the same thing if you assume that there is no vertical degrees of freedom. Like if you assume that U2 and U4 doesn't exist and we only consider U1 and U3, so all these zeros are going to be taken out and you are going to end up with EA over L, negative EA over L, negative EA over L, and EA over L, which is K. K, negative K, negative K, K. Yeah.
I don't understand why column 2 and 4 are all zeros.
Because the thing is, they represent the degree of freedom U2 and degree of freedom U4. Degree of freedom U2, the concept that we talked about, if this member moved that way, there's no internal forces are going to be generated, so all the forces are going to be 0. And U4 is going to be all 0. Or you can make them like the rows, zeros and zeros. Row number here. This is for degree of freedom 1, 2, 3, 4. Or you can make it U1, U2, U3, and U4. So basically, this is 0, and this is 0. Or you can make this 0 and this 0. And you end up with K, negative K, negative K, and K. Alright? And we just proved that the K, the stiffness, is EA over L. So that's the stiffness matrix of the truss. However, our problem is our truss members are not always horizontal. Sometimes they are like this, sometimes they are with an angle, sometimes they are vertical. So we need to do something about that. So all right, so looking at a trust like this, let's put it here. Yeah. The problem is all these forces are local. What do I mean by local? That's what happened actually in SAP 2000. There is local coordinate systems, if you guys remember. You would have a member like this, so you will have the forces is in the direction of the member. And there is global coordinate system, which is measured to the 0 and 0, 1, 0 and 0 for the SAP, and it's something like this, in this direction. So the thing is, to solve the system of the truss, we have a local stiffness matrix for this member, and a local stiffness matrix for this member, and this member, and this member. But the thing is, at the end, I want to convert them in one global coordinate system. Okay, because this system is going to be like something like this, and this one is this, and this one is this, and this one is in this direction, and this one is in this direction. So everyone has its own local coordinate system where we develop the stiffness matrix. This one. Okay, so I have to convert the stiffness matrix of each member from a local coordinate system to a global coordinate system. I put here the proof, like I put something, I'm not gonna prove it because it's gonna take a long time, but I'm gonna just give you a hint. So that's what we proved in a little bit. Like we had a trust member like this. But the thing is, our reality, our trust member is something like this, all right? So I wanna transform this or this from a local coordinate system to a global coordinate system. So basically, like looking at the forces, like, all right, I'm gonna put it here. I'm gonna give you this hint very quick. So basically, what I did here, imagine with me that I made this member like this. So your U's are gonna be something like that, right? And the forces as well. But the thing is, what I'm looking for in a global coordinate system and final forces and final deformation, I'm not interested to get the deformation that way. I'm interested to know how much displacement down. And the same thing, the forces, I want to get them like this. So you need to know what is the angle here, what is theta here. And once you know what is the theta of the member, you can actually, let's say that you have F1, F2, F3, F4, and you want to convert them to F1 capital, F2 capital, F3 capital, F4 capital. So you have to get the component of this. So you're going to say, oh, I have here F1 cosine theta, and I have here going up F1 sine theta. And the thing is, you have another theta here because this angle equal to 90 degrees, so this is going to be theta. So you're going to have here F2 cosine theta, and you're going to have here F2 sine theta. So the thing is, F1 is going to be equal to F1 cosine theta minus F2 sine theta, and F2 is going to be equal to F1 sine theta plus F2 cosine theta. So we are going to have a bunch of geometry here. So, but I'm going to make it very easy for you. Let's say we only are going to talk about this point. So let's say that we have F1 and F2, and also this is a frame member, has F3, which is a moment. The moment doesn't matter because the moment in the global coordinate system is the same like a local coordinate system because it's a moment. You don't have to convert it X and Y. So here there is something that we say F1 global and F2 and F3 at this joint is going to be equal to C negative S, and C, sorry, I need to make it here 1, 0, and this I'm gonna make it SC0, 0, 0, 1, and I'm gonna make F1, F2, F3. What is this? This is called a transformation matrix. It transforms the local forces and the local deformation to global deformation. And that makes sense. Look, if you multiply this vector by this vector, so you are gonna end up, the C means cosine and the S means sine. Okay? This is cosine theta, and theta is the angle measured from the positive x all the way up. So F1 cosine theta minus F2 sine theta plus 0 multiplied by the moment, because the moment doesn't get a component. So this is actually, it's going to give you this one, because this one is F1 cosine theta minus F1 sine theta. Sorry, minus F2 sine theta. Same thing, if you want F2 is going to be equal this line multiplied by this line.
Wow.
F1 sine, F2 cosine, and F3 multiplied by 0. If it's a moment, so the moment is not going to get any components. So F3 is going to be equal to 0 multiplied by F1, 0 multiplied by F2, 1 multiplied by F3. So this is called T, transformation matrix. This is called the global forces. This is called the local forces. Okay? So this is really, really important concept in the stiffness method, that we need to transform all our forces and all our deformation and all our matrices from a local coordinate system at the member level to a global coordinate system at the structural level. Okay? So this is only for this joint, but if you want to build it for the whole member, so you are going to end up with 6 by 6. Like, let's say this is, I'm going to make it for a general member, F1, 2, and I'm going to make moment 3, F4, 5, and I'm going to make moment F6, assuming that this is a frame member. And the thing is, if it's a truss, you just cancel one row and you're going to end up with this too. You will find a lot of details about it here, but I don't want to waste the lecture time. You can read it here, how we convert the whole thing. So I'm going to write here, if it's 6, if you want to do it for the whole member, so we want to have F1 and F2 and F3, F4, F5, and F6. So you're going to end up with a stiffness matrix.
That's a big one.
That's the transformation. This is called not a stiffness matrix. This is called the transformation matrix that transform the local forces F1, F2, F3, F4, 5, F6, transform them to the global matrix. I'm going to divide this into 4 quarters, and this is going to be here. So you're going to end up with C0, SC0, 0, 0, 1. And the thing is, any force here doesn't contribute to anything here. So you are going to end up with a bunch of zeros here. Because the thing is, the components of these forces doesn't affect the component of these forces. So you multiply F4 and 5 and 6 by zeros. Okay, here the same thing, 0, 0, 0. Because these forces here has nothing to do with the forces here. And then you are going to end up with the same matrix here. C, negative S0, SC, 0, 0, 0, 1.
Do we need to remember this, or will you
I'm going to give it in the exam. This is the transformation matrix, and this is the global force, and this is the local force. So it's only one rule. If you want to get the global forces, there is a matrix. I'm going to give it to you. Multiply the local forces with it. That's it. So that's actually for just a transformation matrix for the forces. Same thing apply for the deformation. So F vector equal to a matrix T multiplied by a local forces. Same thing, if you have a deformation, the deformation vector is equal to the same transformation matrix multiplied by the local deformation D. Like if you have a local deformation in the direction of the member, it can apply the same rule. Anything that you are looking at, either forces or deformation, you multiply by the transformation matrix. How about the stiffness matrix? I want to find a global stiffness matrix for this member. This is local, by the way. The one that we got here, this is local stiffness matrix. What does it mean by local? Like your member has to be like this. If your member has an angle theta, this is not gonna apply. Okay? All right. So let's see how we can get a global stiffness matrix. Well, let's get here. I'm gonna get it from here. Okay, this is F vector equal to a transformation matrix T that I already know, multiplied by the local forces. I know that any force is equal to stiffness multiplied by deformation. And since this is a global force, so the global stiffness matrix K that I don't know, and I'm gonna make it big K, multiplied by global vector D displacement, that's all global, is equal to the transformation matrix multiply, this is local, so I'm gonna here have K small local stiffness matrix multiplied by D, all right? So the thing is, this is a global forces, so it's gonna be a global stiffness matrix multiplied by a global deformation. This is a local force, so you have a local stiffness matrix multiplied by the deformation. I already know that the deformation global is equal to transformation matrix multiplied by D, so I can put here K global equal to, multiplied by, I'm gonna put D as transformation matrix multiplied by the vector D. And here I'm gonna have transformation matrix, and then I'm gonna have K, and then I'm gonna have D. Basically, you can divide or D, but we don't say divide by D. We multiply by D transpose or something. But you can say I'm gonna slash this D with this D. So you are gonna end up with K, T, T, K. So the thing is to get rid of the T, let me write it here.
Can't you do the same for the T?
The T is a matrix, it's not a vector. So you multiply by the T inverse. Here, T, oh, okay, I'm gonna come to you in a little bit. The thing is, the T is after the K, the T is before the K. You cannot do that in matrix. They are not at the end. Like, the thing is, I'm not sure if you remember, you guys from the matrices, the position of the matrix matter, either before or after. It's not like multiply two numbers together. So the way that if I want to get rid of the T, I multiply from the right by T inverse. So if I multiply by the right by T inverse, so I'm going to end up with K, T, T inverse, and here I'm going to have T, K small, and T inverse. Right now you can slash these together. If you multiply T by T inverse, they are going to be gone. So you are going to end up with the K global stiffness matrix is equal to the transformational matrix multiplied by the local stiffness matrix multiplied by the inverse of the transformational matrix. So this is how you get K. So T small k, T inverse. That's why I didn't want to get you all that. I want to, at the end of the day, all what I want you to know, that if you want to get a global K, you have to multiply two matrices together. Are you going to do this in the exam? No. I'm going to give you the global K right away.
Thank you.
But this, you have to know where it came from. You have to know how we came to this. So what I'm going to give you in the exam is K, the global stiffness matrix, is equal to, let me take EA over L outside. And here, this is only for truss. We're going to talk about truss now. So, and this matrix is going to be equal to, look here, you're going to find three matrices, the transformation matrix, the local stiffness matrix, and the transformation matrix. You have, that's a lot of multiplication. You have to multiply these two together, and you come up with one, and then multiply it by this third one. It's going to take at least an hour to finish the multiplication of 6 by 6 matrices. Okay, so at the end of the day, all what I want you to know that a member can have a global stiffness matrix K, and this matrix is going to be something like this. And since this is a truss, so it's going to be 4 by 4, not 6 by 6 like a frame. So you are going to have cosine square, cosine sine, and cosine sine, negative sine squared, negative cosine squared, negative cosine, sine, negative sinus, negative cosine, sine. Sine squared. This is not negative, this is positive. Alright, so that's the stiffness, the global stiffness matrix of any truss member at any angle. And by the way, this angle has to be measured from the positive x because this is the way this one has been developed. Like if you remember like this is gonna be your angle, theta, and you need to find 120 degree, and this is what you are gonna substitute with. Let's assume that your angle is 0. What does it mean by the angle is 0? That like your member is like that, which is the local member. If your angle is 0, theta is equal to 0, what is the cosine? 1. What is the sine? 0. So any element here has sine, has s is gonna be 0. So c is gonna be 1, 0, 0, 0, negative 1, 0, 0, 0, negative 1, 0, 1. So you are gonna end up with 1, 1, negative 1, 1, negative 1. The same thing, multiplied by EL is gonna lead you to the local stiffness matrix. Same thing, alright? So this is actually all what you need. The global stiffness matrix. We need to forget about the local unless our member is horizontal. Even if the member is horizontal, I still can use this. Alright? Okay, let's solve an example and see. It's gonna take a long time to solve this example. Alright, so I'm giving you a truss.
I thought that was a water bottle.
No, sir.
Bruh, that's crazy.
My foot has.
Oh shit, sorry. My God.
Say 5.
5 feet. Oh wait.
One more guess. 4 meters.
Force ton. Foot ton. Or not
And
foot
this
ton.
is 3 meters.
Force ton.
So I have 2 ton here, I have 5 ton here, and I want to find the internal forces on these members. We might use these 3 boards to solve this example, but you are going to learn a lot.
It is 5 feet. Like
Oh, sorry, this is ton. Sorry. That's what you meant?
Yeah.
I thought they were guessing.
No, I was guessing if that was like force ton
Yeah, definitely it's 5 ton. Okay, so in this problem, for the shown truss, find the internal forces in the truss member. And by the way, when I ask you to find the internal forces, I want you to find tension, compression, and how much is the tension. But the thing is, at the end, we are going to be in the confusion. Are we going to leave the forces in a global or in a local? We're going to find out at the end how we're going to do this. But to solve this truss, we have to convert all these local members into a global coordinate system. But before I do this, you guys remember the stiffness method rule that F nodal vector is equal to the F fixed end forces plus the stiffness matrix of the structure S multiplied by the deformation vector. That's the general rule. And remember, all what I was teaching you right now was only about the stiffness, like the stiffness matrix of the member and the stiffness matrix of the structure. Okay? So we need to find what is the nodal forces and what is the fixed end forces. And before I do this, number one, if you go to the steps that we have, find the degrees of freedom. Right? So how many degrees of freedom that I have in this structure? 2. Where are these 2?
Up there.
Here. This one can move U1 and this one can move U2. That's the only 2 degrees of freedom that I have. I'm gonna number the members. I'm gonna call this member is number 1, this member is number 2, this member is number 3.
Quick question. So we don't consider rotation as a degree of freedom?
In trusses, no. Because the thing is, because there is no moment. We only consider rotation if we want to find the value of the moment. All these members are allowed to rotate. So in trusses, we don't consider rotation. That's why even the IS that we were calculating doesn't account for rotational degrees of freedom. And there is no moment reaction. All right, so degrees of freedom is 2, equal to 2, which is U1 and U2. So we need to find the F nodal vector at each one of these degrees of freedom. What is the nodal forces at these degrees of freedom? What is the nodal forces? Nodal forces, direct forces in the direction of the degrees of freedom, or direct loads. It's obvious. I have 2 in the direction of U1 and -5. So 2 is at U1 and 5 is at U2. How about fixed end forces?
Reaction.
Fixed end forces only happens if I told you in the middle of this member there's a force applied like this. So you have to fix the degrees of freedom and find how much reactions are you going to have. Since we don't have any forces in the middle, there is no any fixed end forces. They are zeros. This mainly happen, the fixed end forces happen in the beam when we calculate flexure stiffness. Because there's a forces in the middle affect the actions at the degrees of freedom. Okay? So, but in the case of trusses, we don't have this case. Most of the forces are nodal. There's no fixed end forces. Only in one case, if you have a force in the middle, like there's a force here, applying that way. Okay, but we don't have this case. So fixed end forces are 0. So I found these 2. I need to find the structure stiffness matrix to find what is the deformation in U1 and U2 direction, right? So this is actually going to take a long time, but let's see how we are going to do it. So to do it, first I need to get the member stiffness matrix in a global format. So I'm going to start with member 1, but let me write here number 2, structure stiffness matrix. And I'm gonna start with member 1. So for member number 1, our member is something like this. All right? And this member, by the way, doesn't have any degrees of freedom here. This is 0 and this is 0, right? You only have U1 here and U2 here as a global degrees of freedom. But you need to find what is the property of this member. Like what is the length? What is the E? I give you in this problem. Here, top. E equal to 2100 ton per centimeter square, and the cross-sectional area is 13.2 centimeters squared. So it's very easy to get the theta here, right? If you know that this is 2.5, and if you know that this is 3 meter, you can get tan theta, and then you get the inverse. So theta of member number 1 is equal to tan inverse 3 over 2.25, and this is going to give you 53.13 degree. So I got theta 1. Length, you can use the Pythagorean theory, and then you can find the root square of 2.25 squared plus 3 squared. So the length is going to be 3.75 meter. And then E is given, and A is given. What else? Oh yeah, once you get theta, you need to get the cosine and the sine, the C and S. So cosine theta is equal to 0.6, and sine theta is equal to 0.8. And why I'm getting this? Because I want to substitute in the global stiffness matrix. Okay, so right now I'm ready to use the K that is going to be given in the exam. So K of member number 1 is going to be equal to EA over L, and then I'm going to have a big matrix like this, and I have to put all the cosines and sines. But I'm going to tell you a trick. You don't have to write them all. Why? This is going to be too much work. You need to write the things that you are going to use. What do I mean by that? Like, I'm going to divide my matrix into 4 quarters. And where the degrees of freedom are zeros, I'm going to leave this empty. I'm not going to write something here. And I'm going to write where the degrees of freedom has values, U1 and U2. And you are going to find out why did I do that. So you can also do this, 0, 0, U1, and U2. So the cosine, I believe the can you guys, cosine square or negative
Yeah,
cosine?
cosine square.
Negative, right?
No, positive.
He doesn't trust me.
This one. I'm talking about starting from here because I'm not going to write this.
No, but you said 0
Which one?
up there, no?
Just wait.
Yeah, but I'm not going to write anything here. I'm going to start from here.
But what about the 2 zeros in this horizontal? They don't affect it?
Oh, no, we just need these 2 columns. And I'm going to tell you why do we need the columns.
Okay.
We will need these, okay? But these, we are going to need them later.
Okay.
Okay, so let me,
Negative cosine square.
negative cosine square,
Negative cosine sine. Negative cosine
negative
sine.
cosine sine, negative cosine
Negative
sine.
sine square.
And then here,
All of the same positive. So
cosine sine, cosine sine, and then you have
Sine.
sine square. So you can calculate EA over L here. It's gonna save you a lot of time. Like you calculate EA over L and get the value. You have E, you have A, and you have L, and pay attention to the units. This is meter, this is ton per centimeter square, and this is centimeter square. So once you do this, you're gonna have a matrix like that, and I'm gonna make this, and the values here negative 2, 6, 6, 1.12, negative 3, 5, 4, 8.16. And this is, the thing is that the numbers is gonna be like each other. Once you have cosine square, sine square, cosine sine, is gonna be negative 4, 7, 3, 1, and this one negative 3, 5, 4, 8, 2, 6, 6, 1, 1, 2, 3, 5, 4, 8, 3, 5, 4, 8, and 4, 7, 3, 1. I just copy piece and I change it, the whole thing. So I'm gonna, like the signs U1, U2, 0, 0, U1, and U2. And I'm gonna do the same thing for all the other matrices, for all the other members. This member is very easy, member number 2, because it's vertical, and when it's vertical, the L is equal to 3 meter, and theta is equal to
0. Or 90.
90 degree. The cosine
0.
and the sine 1. So I have all these, and I also have E, A, and then you can get EA over L. And once you have this, you can calculate K2, and K2 is gonna be,
EA over L.
okay, this member is the same thing. All the members, we are lucky that we have zeros, and then U1, U2. And then if you have the sine, the cosine is equal to 0, so this is gonna be 0, 0, 0, 0, 0, 0. And this one is going to be negative 1 multiplied by EA over L. By the way, this is not squared. This is K of member number 2.
Yes.
So this is going to be 9,240, 9,240, which is EA over L. Try to 2100 multiplied by 13.2 over the length of the member, which is 3 multiplied by 100. Try to find this value. Okay, so that's K2. And then we need to find K3.
The sine square, yeah, I guess. Yeah. Is that sine negative?
Hmm?
Yeah, it should be negative.
Which one?
The
that 9240 and the top?
Yeah, that's.
Professor?
Yeah.
Quick question. Can you explain one more time why we have like 0, 0 and then U1, U2? At the
This
top?
one?
Yeah.
Because the thing is, looking at, you can actually write here. There's values here. Like if you calculated the values, there will be a lot of values here. But the thing is, I didn't want to put effort in writing them because I already know that the degrees of freedom here are 0. And when we build the structure stiffness matrix, we were only going to focus on this, the ones that has U1 and U2, and the one that has U1 and U2 and plus all of them together. So it didn't make sense for me to do all this writing, and at the end of the day, I'm not going to use them. Okay?
Yeah.
But there's values here. Like the values here, if I didn't put them 0 because I know there's values, but I put the U1 and U2 equal to 0, that means I don't have to write them because I'm not going to use them. All right, so for K3, this is a tricky member because the angle is obtuse angle, like something like this. So you need to find, you need to find this theta, but you have to use this phi, which is 180 minus theta. So once you solve this, you're going to find that theta of member number 3 is going to be equal to 143.13 degree. And the cosine is going to be equal to negative 0.8, and the sine is going to be equal to 0.6. The length of this member is 5 meters, and then E is given, A is given, and you can calculate EA over L. And same thing, we're going to find K3, and we are lucky that looks the same like the other one. They all these members have their local U1 and U2. These are zeros, and they only have degrees of freedom at the other end. 0, 0, U1, and U2. Once you multiply it, EE over L, and then you come up with the matrix, you're going to find out that this is negative 3, 5, 4, 8, 2, 6, 6, 1, 2, 6, 6, 1, negative 1996. By the way, you are gonna find out that they don't match these negatives, like the 4 of them is not negative because we already have some cosine is negative here. So when you multiply with negative, some stuff is gonna be positive. So 5, 3, 5, 4, 8, negative 2, 6, 1, 1996. All right, that's the matrix. All right, so we have the stiffness matrix of each member. I don't need the stiffness matrix of each member. I need the stiffness matrix of the structure. So to develop the stiffness matrix of the structure, and by the way, the stiffness matrix of the structure is 2 by 2. Why? Because the structure has only 2 degrees of freedom. So if the structure has 6 degrees of freedom, it's going to be 6 by 6. But the structure only has 2. So basically, you need to sum the values that are at U1 and U2. Like I'm gonna look at the matrix number 1, so I need to find this, that is the most important for me. And this, the ones that has U1 and U2 and doesn't have zeros. And this one. This is the most important one, where all the stiffness of this member contribute to the node that has the degrees of freedom. So all what you are gonna do now is to sum all these numbers. Like you sum this number with 0 and this number. So when you do that, so you're going to have here this one has 3 values because you have this 4700 plus 9200 plus 1900, so you're gonna have 4731 plus 9240 plus 1996. So you have to calculate all these values and you're gonna end up with 2 by 2 matrix. this matrix is going to be 6209, 887, 887, 1596. Right. So I have S here. So that's what I want for the last element of this equation. I have Fn, I have Ff, I have S. I want to find the value of D. You can use your calculator. I'm not sure if your calculator can calculate this. Like if you have, because if you have your variables here, you can put the equation in the calculator, but the calculator, if the variables is here, can't do it. But you can get the inverse, right? But you guys have solved these equations before, like when you can build these two equations and solve them. It's just two equations and two unknowns. Like basically, you are gonna have, what is the F nodal? That's 20 and negative 50.
Oh, wait.
0.
Wait.
No,
Right.
it's just 2 and 5.
Oh, 2 and 5, sorry. All right. And here I'm gonna have 6209, 7887, and then 15. And then I'm gonna have here D1, or you can call it U1. This is what we're looking for, U1 and U2. So basically, you're gonna have an equation that says 2 is equal to 6,000 multiplied by U1, 800 multiplied by U2. The second equation is negative 5, and this multiplied, so it's gonna be two equations and two unknowns. You can solve them, or basically, you can get the inverse of this and multiply by inverse here. There's multiple ways to solve two equations and two unknowns. Okay, I solve it with the inverse way, but actually you can take the components of the equation and solve them out alone. So you're gonna end up with U1 and U2 equal to 3.7 multiplied by 10 to the negative 4 and 3.34, and it's negative multiplied by 10 to the power negative 4, and all these are in meter. That is the deformation. Actually, the deformation makes sense, right? Look at that. We assume that U1 is going that way, right? U1, when it goes that way, it's gonna go that way because you have a force is taking it that way. And we assume U2 is going up, which doesn't make sense because 5 is going down. So that means that the U2 is negative, which is in the opposite direction of the assumed one, right? Okay, so right now, are we done with the problem? No, we are not done with the problem because I asked you to calculate the internal forces in these members. All what we got is the deformation. So once you get the deformation, you can calculate the forces in the member. If you guys remember when we did the spring last time, that the force in any member, F, is gonna be equal to the F fixed end forces multiplied by, plus the stiffness matrix of the member multiplied by U at that member. So if you wanna find the force of member number 1, and by the way, all this is still local, like F member number 1 is gonna be equal to the fixed end forces of this member, which is 0 already, plus the stiffness matrix of this member. The stiffness matrix of this member is K1. K1 is here, so you're gonna put this K here, and this is 0, 0, and then I'm gonna put the same numbers again. Can you guys tell me the numbers? I'm not sure if you can see it.
Yes,
Let's round it.
Negative
3548.
Here.
Negative 3548. Negative 4751. 31 actually. 731.
Okay, here is gonna be
2661.
Same thing, just public.
Yeah.
alright. And then I'm gonna put U's. Alright, let's see this member. What U's does he have? Has 0, 0, and have U1 and U2. So you're gonna end up with having 0, U, and 0, because this member is having here 0 and 0, and here has U1, U2. So I'm gonna put U1, which I got already here, is 3.7 multiplied by 10 to the power negative 4, and negative 3.34 multiplied by 10 to the power negative 4. That is the U. And here U1 and this is the U2. That's why, if you remember, why did I keep these even that I have zeros here? Because when I multiply this row, it's gonna be multiplied by two numbers here. But here I don't need that. Like if you have a number here and a number here, they are gonna be multiplied by zeros. And same thing here, it's gonna be multiplied by zeros. Same thing with the stiffness matrix. I only used this rectangles. I didn't use this, I didn't use this, and I didn't use that, but I had to write it because I'm gonna use it here. So when you do this multiplication, you are gonna end up with some numbers here, and this number is 2.2.267, negative 0.2, and negative 0.267. Alright, so let me put this trust member here. And let me put the forces that we just calculated. So I'm saying that at point number 1, I have 0.2 force like this. Can you guys see the green?
Yes.
Okay. So, and then I have the force in this direction is 0.267. And then here is negative 2, like this, 0.2. And here is negative 0.267. So the only way to know that you did your problem right, if the forces here is equal to the forces here and in the opposite direction. That means like this member is stable. You have 0.2 here and you have 0.2 here. You have this going up, they have the other one going down. But the thing is, these forces doesn't tell you what is the tension and the compression here. So the thing is, you need to convert these forces from global to local so that you can know how much force that you have here and how much force that you have here. Definitely from what I see, is this member under tension or compression?
Compression.
Compression, right? Because the forces is going that way. And actually that makes sense because you have 5 is going down and the 2 ton cannot overcome the 5. So this member is gonna be under compression. So if you wanna find this force, so the F local, we said before that the F global is equal to the transformation matrix multiplied by the local force vector, right? So if you want to find F, you have to multiply both of them from the left by the transformation matrix transpose, inverse. And by the way, the inverse is the same like the transpose because it's a symmetric matrix. Okay, so if I said inverse or transpose, they are the same. So do you guys know what is the transpose is? You just convert the rows to columns and the columns to rows. Okay, so if I multiply this from the left by T inverse, you are gonna have F, and then here you are gonna have T inverse, T, and then you are gonna have F. So these are gonna cancel each other, and you are gonna end up with the F local is equal to T inverse multiplied by
F.
the F capital. So if you want to find F, you have to get the transformation matrix transpose or inverse and multiply them by these forces, 0.2, 0.267, and negative 0.2 and negative 0.267. So based on the theta that we have here, we got the cosine was 0.8 and the sine was equal to 0.6. So if you guys recall, it was cosine, sine, all these were zeros, that's the easiest part, and all this was 0. And here was the thing. So you are gonna have 0.6, 0.8, negative 0.8, 0.6, 0.6, 0.8, negative 0.8, and 0.6. The thing is the transformation matrix, it was 0.6, negative 0.8, but after I transpose it, the negative came here and the 0.8 came here. So basically you convert the rows to columns to get the inverse. If you don't recall this stuff, try to revise the matrix analysis, okay? So if you have a matrix T is equal to A, B, C, D, if you want to get the inverse, knowing that the inverse is equal to the transpose, not all the matrix is the inverse equal to transpose. It has to be a symmetric matrix, like this number is equal to this number. So it's gonna be A, C, and here you're gonna equal B, D. So C is gonna come here and B is gonna come here. All right, so you do this multiplication, and once you are done, you are gonna find the value here is equal to 0.336, and the value here is equal to 2 multiplied to the power negative 4, and here is equal to 0.336 negative 2 multiplied to the power negative 4. Okay, so this is my member. That means that this member has a force here, like if you do these two forces, you are gonna find out that this force is 0.336, and here you are gonna have 0.336. How about this force? This force is actually 0, and this one is 0. It's just a rounding error from the rounding that we have here, because the thing is the truss member doesn't have any forces that way. It's either a compression or tension. But why did I get a number here? Because I did some rounding. If you did rounding to the force number, you're gonna have a number in the force number. If you did rounding to the 8th number, you're gonna end up with a force in the terms of 10 to the power negative 4. So basically, this number is very, very small compared to this one. Like this one is like, I don't know, 10,000 times this number or something. Okay? So this one is equal to 0. And this is how I got the force in this member. And this is the same thing, you have to do it with every member, like the same way that we did it here. If you want to get the force in member number 2, so we're going to do F, fix it in the forces, plus the stiffness matrix of member number 2, plus U at 2. Fix it in forces are 0. The stiffness matrix of member number 4 was very easy. You guys remember? Because it has cosine is equal to 1. Cosine is equal to 0 and sine is equal to 1. So you only have a bunch of zeros. All this is zeros. And I believe.
Yeah, 3 zeros there.
And was number here?
Yeah.
No.
So what was?
On the other side, you do 0, 0.
No, there was a number here.
No.
Yeah, but it's on the right side.
To the right side.
Oh, yeah, sorry. We don't have numbers here.
Yeah.
This is 0, 0. This is going to be
0, 0, and then
negative
9,
9, 2, 4.
0.
And
Same
this is
thing for
1, 2, 0, 0, 0, 9, 2, 4. That's an easy one. So I'm gonna only have to do is to put the degrees of freedom. So I have 0, 0, and 3.4 to the power negative 4, and negative 3.34 to the power 4, and then you multiply this.
Wait, okay.
Yeah. Oh, 3.7. Not 3.4. So this is gonna be multiplied by this. So you are gonna only end up. This is gonna be 0, and this is gonna be only multiplied by this number. So this is gonna be 3.09 and 0 and negative 3.09. If this is the opposite sign and in the same values, that means that we are in the right direction. So if this is my member, so my member is gonna have, by the way, this is gonna be global end forces. Look at that. So I have the X here is 0, but I have a force here, right? And this one has an X0 and have a force here. So this is 3.09 and this is 3.09. And by the way, I don't have to convert it, because the thing is, this is the same thing like the local one. So this one is having a compression, so it's negative 3.01. I'm not gonna do the last one, but the member 3 is here, and you're gonna find.
You still have a board there? You can use
Well, I
it.
can. So, sounds like it wasn't enough, right? It's 3 boards. It's one of the biggest problems. Gonna have a lot of points in the final exam. So, but by the way, it's long, but it's a systematic. If you are systematic, think about it. Find the degrees of freedom. Get every member alone. Find the geometry: L, theta, cosine, sine, E, A, and L. And then build the local stiffness matrix and do member 2, member 3, whatever, member 4. You keep building stiffness matrix, and try to locate where are the degrees of freedom on the stiffness matrix, and try to focus where the degrees of freedom is, and make a box so you don't forget. And you have a box here, a box here, a box there, and try to collect all of them together to build the structural stiffness matrix. Once you have it, it's only one equation that we are dealing with. The force is equal to the fixed end forces multiplied by K multiplied by U, either a structure or an element. So do it like step by step. It's long, but you are gonna get to the end, like, you know? You're not gonna die. This is really, really important. Next time we're gonna do frames. Maybe we're not gonna go in deep in the frames, but it's gonna be another final exam question on the frames. Okay, so right now we are gonna have in the final exam, we're gonna have one on the springs, one on the method of consistent redundant or the flexibility method, one on the trusses, and one on the next lecture. 4 questions. This one might be the one that has most of the points, like maybe has 35% of the points. The quiz is gonna be on the springs. Okay, so when do you guys want the quiz?
Wait, we're asking.
The springs is the easiest one.
Yeah.
Yes, springs and yes.
Do you guys think the spring is the easiest one, or the flexibility method is much easier?
Actually, flexibility method.
Really? The flexibility method?
I think. Well, if you use those tables that give you the deflection, you don't have
Things
to
you have to
solve the
go,
deflection.
you have to have a main system, and you have to go unit load, and you have to bunch of bending moments and get in tables.
Yeah, no, springs better.
You definitely are gonna do a mistake in the.
Spring, yeah.
Okay, so springs. Do you guys want the exam next week, or because I'm not sure you guys
Not next
are gonna
week.
travel? So how about if I post the exam on Friday?
Wait,
Wait,
post.
I'm confused.
The quiz, sorry.
Oh.
The quiz is an exam still, so.
Okay.
This Friday?
Wait.
Yeah, so that you guys have the Thanksgiving week off,
Yeah.
like, I'm not sure if you're gonna be off, maybe you're gonna work.
Wait,
This Friday
is it
works
a
for
one-day
me.
quiz? It's a one-day quiz.
Friday is tomorrow, right?
Yeah.
So you like tomorrow?
It would be open
It's
just for the
online. Yeah,
day.
it's online.
Open for the whole day,
Yeah.
and you can take it any time during the
Sure,
day.
yeah.
So only
Is that-
so only open for tomorrow.
Almost gonna open tomorrow. If you guys don't want that, the thing is it's springs, like.
That works
That's
for
okay.
me.
Everybody agrees
Right?
now?
I just don't want you, like, maybe you are on a Thanksgiving or traveling or something, not on Tuesday, but if you want Tuesday, that's fine.
No Tuesday.
No, I think.
Okay, so tomorrow I'm gonna post the exam, right?
Alright.
Alright.
Just go first.
Yeah, it's a quick.
It's just 30 minutes, it's not
Yeah,
that much.
20-minute quick.